Okay, recording has also started. Okay, so let's get started with the session. This is primarily to discuss any doubts that you may have in weeks 1 to 4. We'll be happy to answer with respect to the quiz. If you have any preparation related doubts, please do feel free to ask, or concept related doubts.
Also, you can ask about assignment 1, graded assignment 1.
Assignment 1 is also launched.
Swaminathan sir.
Yes.
Yeah, last week we discussed, several points. So, did you get some time to go through that?
Yes. First thing was the recorded sessions were not available on the portal, right?
Yeah.
So I think now it is available, I guess.
Yeah. Anyhow, those are the administrative points,
Okay.
like concept related.
Yeah, we will cover it this week.
Okay.
I think one was with respect to elasticity. There was a negative sign, right?
No, that was explained on that date. So, I discussed. I think Rajesh had asked.
Okay.
Anyhow, if Rajesh is still having that doubt, so Rajesh can ask. Otherwise, that was clear. Yeah. So apart from that, there was consumer surplus point one. That point was there. Then in chi-square test, I had asked that we check for independence.
Yes.
That part was there. And then I had also asked question related to the difference between this coefficient of determination and correlation coefficient, right? How to interpret. So there were 4 or 5 questions. Let me find it out. If we let me find it out. Any others can start. Yeah.
Sir, in graded assignment, I have one clarification question. Can I ask?
Sure, please.
My question is related to the question number 10, which is with regards to the sales.csv data. Again, I don't know if I can ask this question. That file is having 2 columns actually.
Okay.
One is the year, another is the sales. But however, it's not very clearly specified, what to use as a dependent variable and independent variable. Are we good to consider sales as a dependent and year as an independent variable there? I just thought of clarifying it.
Yes, you can do that. In fact, a similar thing was covered on last week's live session. If you remember, in the last week's live session, I had showed you one savings forecast, savings problem. So it is very similar to that.
Okay, got it.
You can do that.
Sure, sir. Thank you, sir.
Hello, sir.
Yes.
Sir, I was doing some previous year questions from business analytics, and I've found some difficulty in 2-3 questions. May I ask her?
Yes. Malolana is also here. We'll help you out.
Okay, so should I share my screen for that?
Just tell the question. We will give you the concept. Usually, and if you have a discrepancy in the answer, you can just check it out in the discourse, because previous year question paper we would have discussed that all the discrepancy answers which were either errorly marked or there is a logic behind the answer. So that would be discussed.
Okay.
I will discuss the concept with you today. So you can just tell me the question.
So there is a question. The question is, the linear demand response for a product A is modeled as simple linear regression, represented as dp equals to 1500 minus 20p. So dp is the demand. I guess 1500 is d naught, and 20 is m.
Yeah.
So it's asking for the yes, sir. So it's asking for the satiating price.
What is the satiating price?
Yeah. So it is d naught by m.
It is
1500 by 20.
It is a price where the demand is 0.
Yeah. Okay. Demand is 0. So d naught by 20 would be the price. But answer coming out to be 750, and my answer is 75. So
that is 75 only.
Yes, that is 75 only. There was a typo error in the answer which got rectified. So you can just check it in the discourse. We have told it there.
And sir, one more question. There is a graph, sir, a scatter plot with some different models with some different colors. And each color represent a model. So, sir, the answer to this is what message it conveys. The answer is given as relationship between car weight and mileage. But according to me, sir, I think that it is a relationship between car and weights. Just a second, sir.
For different brands.
Models.
Yeah, for different models.
No, it is not. The reason being, if I wanted it for different models, I would have split the graph. This is not a right representation for it, because that if you see, all the plots would have been the points would not have been grouped separately. It would have had a spread. Let's say I had 3 colors: orange, red, and green. Again, this is also discussed in the discourse. You can go have a look at it. Because all brands or all models would have been spread across the entire weight. So there's actually no point in giving that color. It should be only this thing. That is why the answer is, it is a graph between only the 2 variables.
So, sir, for different models, we should have a different graph for each model.
In this case, yes. In this case, because for every model it's spread across, it does not make sense to give it in the same thing. If it was, let's say, if it was specifically grouped in bunches, then it makes sense.
Okay,
Or else
so
you cannot do it.
so sir, like when we want to represent different models in same graph, so which kind of graph is appropriate for that?
That depends on how your data is looking. The same data, if I had clustering, let's say one brand was here, the next was in the middle, then the next was in the high end, then it makes sense. But
So,
if it's spread across, it does not. One second, let me just open the question also. This was which year? Can you tell me which run?
Just a second, sir. I think it's quiz 1 paper of January only.
January 23.
I think it's a 22.
22, January 22. This one.
It's question number 177.
Okay, I will not have that because there will be different sets uploaded. Let me just pull up my essay. Okay, so right. Let me share my screen. Yes. So this is the question, correct?
Yes, sir.
Okay. Here, let's say we have 3 colors: blue, orange, red, and also green. Fine?
Yes, sir.
Okay. So there is no particular pattern that all the blues are in one place, reds are in one place, the yellows are in one place, or the oranges are in one place. So for across all brands, the same trend. As the weight increases, the mileage is decreasing. Correct?
Yes, sir.
So in this case, the coloring does not make any sense. By brand, I cannot say. Irrespective of brand, as weight increases, the mileage is decreasing. So that is the message that I can give.
So, sir, overall, we can say something that the trend is negative and it's going like with the slope downward.
That and all is fine. That and all you can say. But
But for blue, usually,
given the different messages, it is this. The same graph, if I wanted to say for the blue brand something, orange brand something of that sort, then I will have to split. I can have the same axes, but I should have a blue graph separately, orange graph separately, red graph separately.
Yeah, altogether it is messed up on the same graph. That's why
I cannot say, right? In what only thing that you can maybe extrapolate this and say is, irrespective of brand, as weight increases, the mileage decreases is what you can say. But the relationship in this case is only 2-dimensional, so you cannot do anything further.
Okay, and so the next question following that, question number 8.
This one.
No, sir. I think question have been jumbled.
Yeah, it will be jumbled in your paper. It will be jumbled. Can you read the question to me?
Yes, sir. Just a second. So it's for considering a lot of size 100. What is the value of test statistics chi-square goodness of fit? That table mentioned in the main question follows a Poisson distribution.
This one. This one.
Yes,
right?
sir. Yes, sir. Yes.
Okay. Considering, I've given you the formula: observed minus expected the whole squared by expected.
Yes.
Correct. So you will have to, from this table, you will have to find out which is the observed, which is the expected, and then do it.
So, sir, the actual number of items found are the observed.
Obviously.
And the theoretical expected are the expected. Correct. And we have to find the chi-squared value. That's correct. Fine. But how this is going to help us that this data follows a Poisson distribution?
No, the question is, you have to check, it's a goodness of fit question, whether this data is following a Poisson distribution or not.
Yeah.
All right, it's a goodness of fit question. That's a catch here. What is the catch? Can someone tell me?
That is the null hypothesis, right?
No. What is the catch in the data? Let me just check. There's a catch in this data. What is that? I have given you possible number of defects. Let's say you are producing a product. I've not given you the business scenario. I've directly asked you the question. There is a business scenario. Let's say you are producing a product, and in that product you're measuring the number of defects and in a product, okay? And you take a sample of 100 products. You find 1 defect in 12 products, 2 defect in 22 products, 3 defect in 16 products, 4 plus defects in 32 products. There's a problem in this data. That is the catch. Without doing that, if you do it, you will get a wrong answer.
That is frequency, right?
What frequency? The 12, 22, 16, 32 are all frequency, yes. That is the actual observed frequency. The theoretical expected is the expected frequency, but there is a catch. And the information is given to you. You should be careful. When I put 4 marks for a question, obviously there's a catch. And I've given you the formula also. Yeah.
For 0 defects.
Yeah, exactly. When you add up these numbers, this does not add up to 100, which means there are sample points which are not captured. The only way is 0 because I've given you 4 plus. So I can have 0 defects, 1, 2, 3, or 4. And in 0, you should put a number. 100 minus these numbers would be 0. And then you will find out whether it's following a Poisson distribution or not.
So, sir, could you please explain this in a bit detail, how to go for this?
So, this is the formula, all right? Observed minus expected, the whole square. The expected is the formula.
Yes, sir.
For chi-squared from your statistics 101. Here, this is your contingency table, let's call it that. Or this is your frequency table. In your frequency table, I should have a sample of 100 numbers, which means the observed frequency and the expected frequency should add up to 100. In our case, it will not add up to 100. I think this will add up to some 80 or something. This will add up to 70. I just did it. I forgot the number. So let's do that. So you are going to add up 12 plus 22 is 34, 40, 50, 82. Yeah. So this is 82. 100 minus 82 is what?
18.
18. So where will that 18 sit?
0. In case of 0, 18.
Yeah. So there are no defects in 18 products. Now you add up, you will have 100 samples. Same way, do the addition here and find what is for 0.
That is 30. 30.
So 0, 12, 0, 18 and 30 you should add up. Then you will have these numbers. So these are the number of buckets. So the number of buckets for you is 1, 2, 3, 4 and one more which is 5. 0, 1, 2, 3 or 4 plus. So there are 5 buckets. You have observed frequency, expected frequency, compute the chi-squared.
So, sir, in this table, we have to add one more row for the 0.
Yes.
Okay, and then go for the chi-square test.
Computation, yes.
And so, how will get the hypothesis that yes, it is following the Poisson distribution, just looking the chi-square value?
You will not get it from that. That is the test. Always in the test, the null hypothesis is always fixed. That the assumed distribution is what the data follows. You should find evidence against it.
What professor says no effect, like the status quo situation.
No effect is what?
Yes, the given case, the given conditions that we have to, since the question is asking the Poisson distribution, so I have to assume that the null hypothesis is that my distribution is.
The null hypothesis is that it is a Poisson.
Yes.
Find evidence against it.
Correct. So my null hypothesis will be the population follows a Poisson distribution, right, sir?
That is the answer. Yes. That is why it's highlighted in yellow. So the null hypothesis is that the population follows the theorized distribution. You get a sample under that assumption, and then you find whether there is evidence against that assumption or not.
So, sir, when we'll find this chi-squared value, my calculated one, and I'm not having the tabulated one, which was given to us. Yes. So, how I'll be able to confirm that whether the null hypothesis is true, whether we have to reject it or not reject it?
That is why I have not asked you that question.
Okay. So that's what I have to.
That is the
Yeah.
next level. So now you have a
Okay.
test statistic, you know your null hypothesis, then you go and compute the degrees of freedom. What is the degrees of freedom?
Number of rows
Number of
Okay,
into
number of
columns
rows. Number of rows?
Number of data point
-1.
-1.
into columns -1.
No, that is for test of independence. This is test goodness of fit.
Sir,
Remember, there are two chi-square tests.
okay.
This is chi-squared goodness of fit. What you said, number of rows -1 into number of columns -1 is for, I don't believe, is for this one, which is a chi-square test of independence. This is a chi-square test of goodness of fit. How good is the distribution that I proposed? This is how whether these variables are independent. In the case of independence, it is row -1 into column -1. In the case of this, what is it?
Number of buckets minus number of parameters -1.
-1, exactly. So how many buckets? You have 5 buckets. How many parameters?
Poison means 1 parameter.
1 parameter. So 5 minus 1 minus 1, which is 3 degrees of freedom.
Okay, sir. Understood.
Okay. So now you have degrees of freedom. You will establish alpha level. Go to the table, find out your chi-square tabulated. If that is, when will you reject the null or accept the null? Sorry, I should not say accept the null. Bad. When you will reject the null or will not reject the null?
When calculated value is greater than the tabulated one, then we'll reject it.
You will reject the null. Exactly. That is all.
Sir,
So,
if
sir,
the data is not in this table format, only 2 columns, price and demand. How do you calculate chi-square test statistic values?
That is your assignment. I can't tell it right now.
Okay.
So, sir, in this question, what I have to do is just add a row and then do find the chi-squared value.
Correct.
Okay. Okay, sir. Thank you. That's all. Thank you, sir.
Sir?
That
Yes.
is also one of the previous quiz
Hey.
questions, right? That question.
Which one?
Only 2 columns are there. How to calculate chi-square value?
Only 2
Price
columns.
and demand.
Okay, once again, can you tell me the question paper, please?
No, I think it comes from the assignment, Malolan. So if
It
you
comes
look
from
at,
the
Okay.
yes.
Okay, sir.
So, and you,
assignment, we don't want to say.
Ah.
What we will do is suggest where to find it.
yes, I will tell you a simple thing. Srivatsa had done a detailed tutorial on those chi-square test of independence.
Sir, I have a question related to chi-square only, sir. So may I ask at this point of time?
Go ahead.
Sir, am I audible?
Yes, go ahead.
Yeah, sir, as you rightly said, and in video lecture also we have learned that chi-square is used for goodness of fit, right?
It is
So-
used for goodness of fit and tensor of
I am coming to the next point, sir. So, and by that time the video got over, and in the next video, professor said that now we have to, before proceeding for chi-square test, we have to check for independence also, right? So what he did, he applied.
He would not have said that. He would not
Yes,
have
yes.
said that because chi-square test of independence comes in week 3, whereas chi-square test of goodness of fit comes in week 2. Two different.
Okay, so I will find out exact the video number. So let me phrase
Yeah.
my question itself. So this kind of situation was there. Then he said, before checking for goodness of fit, is before applying chi-square, we have to check for independence also. So even for checking the independence, he used chi-square itself.
Correct.
So I got confused a little bit that how come this is becoming a, don't you think that this is becoming a circular case, because for applying chi-square, we have to check for independence. And for using independence, we are using chi-square itself. So don't you think that it is becoming a
No, you have
circular
not
kind of
understood
thing?
it right. No, you have not
Yes, sir.
understood
That's why
it
I'm
right.
asking. That's why I'm asking this question, sir. Yes.
Yeah.
Sir.
So the first thing is, when you are checking independence, it's for categorical variables, right? You are telling whether these variables are independent of these variables. Let me give you an example. Let's say you have a store that sells men's clothes and women's clothes. All right. So you have men's clothes, women's clothes, and these are located in 2 different areas, A and B. You want to see, and you are computing sales. You want to see whether the sales of men's clothes in location A is independent of sales of women's clothes in location A. Sales of men's clothes in location B is independent of sales of women's clothes in location A. Sales of any of these clothes are independent in any of these locations. Okay, so that is test of independence. The variables, the categorical variables of sales of men's clothes, women's clothes, sales of location A and location B, all of these are independent or not studied by chi-square test of independence. That is a different problem. Now comes the distribution. In goodness of fit test, what you will check is, given that I have this kind of sales data over, let's say, over the last 30 days, over a month, I take the sales of number of dresses sold for men. I want to know what distribution that is following. There I will do a chi-square goodness of fit test. I do not know. I do not think that any point in time sir would have said, now that we have to do goodness of fit test, we need chi-square test of independence, or chi-square test of independence needs goodness of fit test. I believe what sir would have said in the video is, now that we have seen chi-square goodness of fit test, let's see chi-square test of independence. That is two different things.
Okay,
that is what sir would have said.
Let me find it out again, sir. Yes.
Yeah, go check. Definitely, yes. This is what would have been. In chi-square goodness of fit test, I want to know whether a given set of numbers or given sample is following a particular distribution. That is chi-square goodness of fit. Whereas in chi-square test of independence, whether some data is independent or dependent, that is chi-square test of independence. Two different things, but the same test statistic. The way it's calculated is also same. Okay.
Okay, sir. So just two follow-up questions to this, sir. So just to summarize whether my understanding is correct or not. So chi-square test is done for two purposes. One is for goodness of fit, and the other one is for testing the independence, right?
Correct.
So, sir, whether we are checking whether two variables are independent or not, only for categorical, or we can do for continuous variable also.
You can, if you can generate the table, you can continuous variable.
Yeah, because
ultimately the variable that is okay. Like I said, the sales variable is continuous.
Correct. Yes, I come to that only.
The sales variable is continuous.
Yes.
But you are measuring that for a category, right?
So those are two features.
Location A, location B.
Those are two features I can say.
Those are categorical variables. Amount of this thing sold in location A becomes a categorical variable. So it's just for categorical variables.
So my variable can be.
Yes. Ganga Prasad, one thing. So if you have two continuous variables, what test you will see to find the association? You can do a two sample t test. And then if you have one continuous variable and one categorical variable, what test will you use?
No, even when I am having two variables, I can go for scatter plot also. No, I can check.
That's a visual medium, and you want to do a statistical test here.
Ultimately, using a visual, you will narrow down. So you cannot say that is a test for me. That is just an assistance for you.
Right. So here, for two categorical variables, you are performing chi-square test of independence. If you have two continuous variables, you will be doing a two sample t test. What if you have one continuous variable and one categorical variable? Can anyone answer?
Not getting at this point of time, sir. I think this we had studied in stats 1 or something like that.
All right. So hold on. So maybe we can discuss this later. Keep this question with you. Think about it, and then we can discuss it later.
Answer, Malwan sir, my second question. It may seem trivial at this point of time, but I'm asking since we have studied, sir, as my sample points are increasing. Say for example, it is more than 30, right? So it follows normal distribution irrespective of the original distribution, right? When
it is an assumption, not necessary.
It's an assumption, right? So the trivial doubt was that when my sample size is large, say for example 100, 200 or 500, so why to even go for goodness of fit? I will simply assume that it is following normal distribution and I can proceed with that.
Wonderful question. This is a fundamental flaw. What happens is your sample is a representation of the population.
Right, sir.
The population need not be as normal just because you got a sample of size 100. Right?
Yes.
That is what it is. So what they mean by when you have large samples is try to remember your statistics. I'm sure that sir would have talked about this. Sir talked about central limit theorem. Do you guys recall?
Yes. Yes.
That becomes normal. So your central limit theorem basically states that your test statistic, your distribution of your test statistics becomes normal.
Sample mean follows normal distribution.
Sample means and sample variances, those follow normal distributions. So you can assume it to be normal. That is the statement. So it is never about the population. That is what you're trying to infer.
But even
goodness of fit test.
but even I can proceed through that route also. I may not get the exact answer, but since my sample mean
No,
is following.
you cannot. No, ma, you cannot, because here there's a difference. Look, in chi-squared goodness of fit test, you are telling whether this population is coming from this sample is coming from a population,
Right, which I don't know.
In test, which you don't know.
Right.
In test of hypothesis testing, basically that this is also hypothesis testing. In, let's say, one sample test, all of those places, you are telling whether this sample with a particular mean is the population mean also the same.
Right.
That is two different questions. Here you are comparing the parameters. There you are telling whether the distribution is this. So there are two different things.
Okay, so what I am getting, that by using the concept of central limit theorem, since my sample mean is following the normal distribution, so I will estimate my sample mean and I will try to infer about the population mean. Am I right now?
Correct.
Okay, I will try to infer about, that's why it is called inferential statistics. So I will try
Correct.
to infer about population, right?
Correct.
Okay, sir. Let others
Here-
ask. Yeah, I got it,
Here,
sir.
here is just a follow-up.
Yes.
Even goodness of fit test is an inferential statistic.
Hmm.
Why? Because you get a sample, you are under the assumption that this sample mean is the true population mean, for example. And then if you then divide it into regions, then you have an expected value, you have a sample value. How far these are away from the expected value? Is it significantly far? Then the only assumption that you can throw out is a null. That is how you confer. So this is also inferential statistics.
Okay, sir. Thank you, sir. Let others ask. Then I have one more question. I will ask later on.
All right. Okay. Anything else from anyone else?
Okay, then let me come back in the queue.
Yeah. Please go.
Sir, while studying regression in week 4, right?
Okay.
Yeah. So when we are testing for beta naught and beta 1, beta naught and beta 1, so I am taking my null hypothesis as that beta naught is 0 and beta 1 is also 0, right? Two hypotheses we are taking.
Correct.
So generally in null hypothesis, what happens? We take the status quo situation or no effect situation, that's what we call no effect or status quo situation. So are we assuming in case of regression that these two variables are not following regression? That's why I'm taking beta not equal to 0. That is the underlying assumption.
Yeah.
Okay, that's the underlying assumption. I was thinking that underlying assumption should be that these two variables are correlated and they can be projected using the help of linear regression.
No.
Okay. So my no effect case is that these are not linearly related, right? That is my no effect case.
It is not that these are not linearly related. They are insignificant for the y.
Sir?
That is the thing. It is not relationship between beta naught and beta
With
1.
respect to y.
It is that
with respect to
y
yeah.
is not getting affected by beta naught, or y is
Okay,
not
so that is my no effect situation, right? That is my no effect situation.
Correct.
Okay, so it is a simple doubt, so that got clarified. And sir, when we say standard error of skewness, I know that standard error measures the standard deviation of variance itself, right? So when we are introducing that term, that standard error of skewness, so what do we mean exactly?
Standard error of skewness, sir.
Yes, sir.
So I think Malulu, when Sir does linear regression in Excel, so it generates a lot of statistics. One is standard error, and then it also talks about
multiple R.
I mean that's nothing but adjusted R square. And when you have more than when you have more than one feature, when it's a multiple linear regression, you will have both R square and adjusted R square.
That is okay. No, he's talking about standard error of skewness.
Yes. So right now you can ignore that, is not of significance to you people.
Yeah, I don't even know where Sir is referring. I'll just check it up. Just put it in the discourse and tag me. I'll have to reuse it. I don't remember any such thing. There might be some audio issue or something. Let me just check it up.
Yeah, answer there are three terms. One is covariance, right?
Okay.
And the other one is correlation coefficient.
Okay.
And then the third one is r square, which is nothing but the square of r, right? Square of r. So, sir, with the help of covariance, we are only saying that whether these two variants are related or not, right? But we are not talking about the strength of relation. I'm just checking my understanding. And with the help of correlation coefficient, we are saying the direction of relation also as well as the strength also.
Correct.
And when I'm squaring the strength, I am getting r square, right? And then now I'm interpreting that as the percentage of variability which is explained by this model, right? So what is exactly meant by this statement that percentage of variability? Say for example, my r square is 0.81, so I will say that 81% of variability is explained by this model. So what does it mean exactly?
It means, given, let's say the model is fluctuating. Let's say you are given a model that is data that is fluctuating. Obviously, data is not stationary. So data, I should not say stationary. Data is not fixed. So it is going to be randomly doing. So using this model, 80% of that randomness is captured. 80% of that random pattern is captured. You will be able to say with 80 that if I do this, 80% is captured. 20% is completely random. You cannot say anything about it.
So that is randomness error. That
not random error. Not random error. I'm talking about something that you. This is the model's. Let's say model's ability to predict the value in a sense, right? When I say 80, I have an R square of 81%. Then what I mean is, how can I tell this? Percentage of linear that is captured, linear variability that is captured.
Sir, that is dependent variable is explained by
81%, but even if I use the word explained, it might still cause confusion. That is what I'm trying to think.
price is explained by the independent variable demand.
Correct. So what?
So Satya, what is that remaining 19%? Whether that is error or what is that?
No, that is randomness. That is random. It cannot be explained. So any model, you have two basic pieces. You have the bias, you have the random. You will always model to reduce the bias and extract as much as information as possible. The remaining aspect is unexplainable. That is why you have errors. If you have 100% explainability, then you will have zero error. So that remaining 90% is randomness.
So then what is the rationale behind squaring it? Because when the correlation coefficient is giving my 0.9 value.
0.9 is your direction. Now, how closely they are related?
No, plus is my direction. Plus means they are positively correlated, right?
Minus point, this number of can be between -1 to +1.
Right.
So it's just telling you the direction of correlation and how closely they are. Whereas when I square, okay, in statistics generally we square for several reasons. One reason is to have a smooth function. And here when you square, basically if you look at the formula for R, it is when you square it off, it becomes much more smooth. And you remove out all the square roots that are there. Then it starts explaining the variability. It's variability. Look, the original R, you can look at something like a standard deviation.
No, original
R
is
squared
correlated
becomes
coefficient, right? Original R is correlated.
Correlation coefficient. When you square it, it's called this thing. R squared is correlation coefficient. Sorry, R is correlation coefficient.
Coefficient of determination. Coefficient of determination.
So coefficient of determination is basically explaining variability. So variability means square. Keep it like that. Because I'm not
So can we say R square is also a goodness of fit?
No. R square. Okay, yes. R square is a goodness of fit for your model. How good your model is?
So what about
linear variability?
So what about the chi-squared goodness of fit?
Chi-squared goodness of fit is for distributions. How good is your prediction about the original distribution of your data?
So this R square is the ability of the model to explain the variability in the dependent variable.
Okay, so for sample, are we using the R squared thing?
No. Yeah, from the sample, you say this, given this sample, if I build this model is explaining 80% of the variability that happens in Y.
Okay.
That is R squared.
Okay.
But let's say you want to know how Y is distributed. That you use chi-squared.
So goodness of fit of model is given by R square, and goodness of fit of distribution of the original data is given by the chi-square.
Correct.
Okay, sir. Thank you.
And sir, once again a conceptual doubt, sir. Like while calculating expected frequency, right? In chi-square test of independence, we are calculating expected frequency as row total into column total divided by total sample size.
Correct.
Row total. So, sir, what is the rationale behind taking this formula?
Very simple. Now it's observed frequency minus
Right.
total frequency. Total
It's
in
not
that row.
It's not minus. That is row total into column total divided by total sample size.
One
Row
second.
total
Row total
into column total.
We are calculating expected frequency.
That's why,
One
sir,
second.
I am
That is
saying
the
what is the
expected
rationale
frequency.
behind that? What is the
One
rationale
second.
behind
That
that?
is the expected frequency. If I'm
Yes, expected frequency. I'm
that
saying.
is the expected frequency. Now,
Yes, yes. So what is the rationale behind that?
I have so much in my column. I have so much in my row. Divided by the total that I have, that is going to be this value, which is going to be expected over there. That is basically the rationale. That itself is the rationale. If you ask me what is more than this, I don't know what to say. So the rationale is this: you have a total in your column. All right, it is split. This column is a categorical variable, row is a categorical variable.
Right.
So this is split, and there is a number here. This is split, and there is a number here, and then you have total number of samples. So what proportion of these two is of the total is sitting there? That is basically multiplication. It's not divided or plus by 2. That does not make sense. So they multiply. How the multiplication comes?
No, generally when we calculate frequency, it is just by observation divided by total sample size, right?
Really?
Yes.
Really? Then why do you take the probability mass function and all for calculating Poisson distribution?
No, I was just asking. I'm not.
No, that is what it is. It need not be always the case. That is why I asked you that question. It need not be always the case. The expected frequency for a Poisson distribution comes from its PMF, the probability of observing something in that point into the total number. Similarly, what is the probability here in this case? This is not in scope for us, but you should have asked this in statistics. So the rationale here is that I have one category which has
chi-square was not covered in statistics, sir. Chi-square was not covered. No, sir. I have attended both stats 1, stat 1. Here I stick to my statement. Whatever statement I am passing on, I am sticking to that.
Okay.
It may happen that in one of the term that was covered, I covered stats 2 in previous term. You can check with Srikant sir and others also.
Stats 1 and stats 2.
Yeah, it was neither covered in stats 1 nor in stats 2. It may happen that in one of the term it was covered because we had also seen some question paper. So where chi-square was there. But when
it was in stats 2, I guess.
It was that.
Srishti, I did stats 2, in September 2022 term, and chi-square was not there, and I stick to my statement.
Fair enough. Okay. It is definitely there. I also stick to my statement. Let us check.
No,
you can post it because I verified. Because what happened was last time people came, it seems, and they are told regression was not covered. Then I went and verified with the team, and regression is covered in week 6 and 7 of this thing of stats 2, I believe. Not MLT, stats.
Regression in stats 2.
In stats 2, it is covered. So if you do stats 1, stats 2, you should have all the concepts required here. So I verified that it is definitely being covered. The basics of simple linear regression is being covered. So I believe you have forgotten. Just go check it once more. All right. Okay. So that is what it is basically, because without covering chi-squared, no one will complete the hypothesis testing.
So just one suggestion to Ganga Prasad. I think he should go to the YouTube playlist, and there he would be able to find an stats 2 course playlist. At one of the lectures would be of the chi-square test.
All right, fine. Let's not get into that argument. But anyhow, just go check it out. It should be there. Or else you can always post a question in stats 2, and people will answer if you want to. We are always here to help. Okay, any other questions, Ganga?
Yes, sir. I'm just finding it out. Just a second. I have jotted it down. So
all right, sure. Anything else from anyone else? It seems to be Like only 3 people have doubts. All the others are good with the quiz one.
No, I'm a laggard, so I always have doubts there.
No issues, no problem. Doubts are good.
And I think your question was with respect to coefficient of variation. Is that correct?
Yes, sir.
Okay. So you want to know some applications of it? Is it not very clear?
For Poisson distribution and exponential distribution.
We covered it last week, right? So what is the formula for coefficient of variation? It's sigma by mu.
Yes,
No,
sir.
that I had not asked. I think Satya had asked that. That's why she is responding.
Yeah, Satya is only answering. No?
What is the value for coefficient of variation for exponential distribution and Poisson distribution?
Okay, so I've given you the formula. Sigma by mu is the coefficient of variation. What is the sigma of Poisson distribution?
Is lambda.
What is the mean of Poisson distribution?
Lambda, both are same.
Okay, so so what will be the coefficient of variation?
1.
Yeah, that's correct.
For exponential distribution?
What is the mean? What is the sigma?
1 by lambda.
What is the
Mean is 1 by lambda.
then? What is the coefficient?
Both are same.
Yes.
Okay.
But
sir.
do you know the applications of coefficient of variation? Was it covered anywhere?
No, sir.
Okay. I'll just give you a simple intuition of coefficient of variation. So let's say you drink a bottled mango juice, right?
So what is the coefficient of variation value? Is high is good or low is good?
Yes. That you should tell me. Is it higher the better or lower the better?
I don't know.
All right. So I'll just give you an intuitive example. Mala, you want to cover something?
No. I just wanted her to think about intuition. It's going to be this thing. Look at the ratio and then just think about it. In the meantime, Swami, give an example also.
Yeah. So let's say you drink a bottled mango juice like Slice or Maaza or whatever, fruity. So every time you drink the bottled juice, does it taste the same?
Yes.
Okay. So let's say you go to IIT campus and you go to a juice shop and you order mango juice. So every time you order, is it going to taste the same or is it different?
Different.
So what will be the coefficient of variation for the bottled juice, and what will be the coefficient of variation for the juice shop?
It may changes.
How? Which will be higher? Which will be lower?
Juice shop is higher.
Yes, and bottled the coefficient of variation of bottled juice
is low.
Yes. So here, which is better? Higher the better or lower the better?
Higher is the better.
How?
Juice shop is good, right?
So here, good means it should taste same every time. So that is good here. So first we have to define what is good, what is bad.
Okay. Tell me the formula again. What is the formula for CV?
Sigma by x bar.
Sigma by x bar. Fantastic. So when the value is high, what does it mean?
Standard deviation is high.
Standard deviation is high. So what does that mean from a process sense when my standard deviation is very high?
Variability is high.
Variance is high.
So when my variance is very high, what does it physically mean?
That is the data points are spread.
Okay. So now you have a process that
from the manufacturing point of view, I cannot rely on my data. I cannot rely on my process.
Data. So something that is extremely highly spread now as compared to your mean means it is not consistently producing something. It's always varying.
Okay.
That is not good for your process. This is where your CV comes. So let's say you have a process. One has you cannot just look at variability. That is the importance here. Let's say one has a standard deviation of 100 and mean of 10. The other has a standard deviation of 100 and mean of let's say 100. Then the CV for the first one is 100 by 10, which is going to be 10. The CV for the second one is 100 by 100, which is going to be 1. Now looking at those numbers, you can obviously say if you just look at variance, it's going to be 100 square on both sides. No inference. But compare it with the mean, this process is extremely accurate, whereas that guy is not.
Okay. Understood.
That is the importance of CV. That is what Swami was trying to say. You want to go to the juice shop, it should always be good. If one time it's good, the other time it's very bad, then the variability is very, very high. Right?
Okay.
Yes, sir.
So
Now may
yeah,
I, sir?
yeah, go ahead.
Sir, there is a case study kind of thing which professor has solved related to brand preference, dependence or independence. So at 95% confidence level, brand preference was showing dependence, right? That like they are dependent on each other. Brand preference.
Okay, I do not remember the result,
Yeah,
but
but the
okay.
moment we shifted our confidence level to 99%, so they became independent.
Fantastic. Yes.
Yeah. So as a practitioner, what should be our approach?
Wonderful question. Now you tell me. Now you tell me the answer. Yeah, alpha affects what in statistics?
Probability of
0.0.
making
No,
probability
that
of
is
making
0.
type 1 error. Probability of
Exactly.
making type 1 error.
So probability of making type 1 error. What is type 1 error?
Yeah, type 1 error states that, say for example, I have taken my null hypothesis, right? So this is the probability that I'm rejecting my null hypothesis, but it is true. I'm rejecting
Exactly.
null
So that is
hypothesis, but
type
it's
1
true.
error.
Yeah, that's type
Correct.
2 error. The type 1 error, yes.
That is type 1 error. So
Yes,
you will reject a null when it's actually true is type 1 error.
correct.
Now comes the question of how to choose an alpha. In general, for all our, at least for our theory question papers, so on and so forth, everywhere, we will use 0.5,
Yeah,
5%,
that,
0.05.
yeah,
That is standard. But from a business perspective, it changes from application to application. Right?
okay,
Let's say you are doing a medical test.
okay.
You are doing a medical test to say whether your person has cancer or not. That is the most common example in any textbook that you take. Or let's say you're doing a test on a COVID patient.
Hmm.
What will you focus on? Will you want a very high alpha or a very low alpha?
I will check for my very low
Let's say
alpha.
your null hypothesis is going to be that the patient does not have COVID, and your alternative is that the patient has COVID. Then what do you want? Do you want a very high alpha or very low alpha?
Very low alpha.
Why?
Like, okay. See, generally my understanding is that for choosing low alpha, that whatever is my null hypothesis, right? It should not happen that I'm rejecting my null hypothesis when it is true.
Hmm.
Correct. So that is the reason why I will take low as much as possible. Probability of making type 1 error should be as low as possible. So that is my level.
In medical scenarios, it's very,
In
very
medical,
important.
yeah, in
Why?
medical
Because if you say that guy has COVID, then you will have to go start treating him for COVID, exert cash amount from him, he has to suffer. So in medical scenarios, the alpha should be very, very low. That is why. So scenario to scenario, it will change. Whereas in manufacturing, I will say, okay, I will go up to 5%. My quality control will take care of the even if I'm wrong. What will I do? I will send it to quality control. They will check there's no problem and send it back to me. In that case, I can go for 95%. Not a problem.
Okay. Because here it's a big change because at 95% brands were dependent and at 99% brands became independent.
Exactly. That is basically shown to you to drive home this point. Nothing else. And this is true for all hypothesis tests.
Right, right. And so for regression itself, we are taking several assumptions, right? Just now we have covered linear regression itself. So we have considered several assumptions like errors should be normal and all those things. So from the application point of view, I'm asking that whether in real life we get this kind of data, because if I'm not meeting my assumptions, right? So somewhere if my assumptions are getting relaxed, so my output will be impacted.
Fantastic. You don't even have to go up to assumptions. In real life, none of your scenarios are linear. Why have linear regression then? That is itself a basic question that arises. The answer to this question is actually very conceptual. What they say is any system behaves linear in a when you take a very small amount of time or small distance. Over a very small incremental distance, it becomes linear. And for those scenarios, you can use a linear regression. And over small distances, these assumptions are still, even if they are violated, they will not get violated significantly, or they will not affect your results very significantly. So in those cases, you will use you will make these assumptions and proceed. That would be my answer in real life cases, because here's where that Occam's razor principle comes into picture. A simple model with a decent amount of accuracy is always better than a very complex model with high level of accuracy. It's Occam's razor in a nutshell. So that is why. Okay. Now answering your question, what is standard error of skewness? Okay, I just gone to the lecture and I opened it up. What that means is you are measuring skewness for your data set, and that measure is also a computed value. And whenever you have a computed value, you will have a standard error for it. That skewness or standard error for skewness is on that computed value. That is all. Its interpretation remains the same. So your skewness can be plus or minus this value, this range.
Thank you, sir. Thank you.
Okay, so that is the interpretation. Thank you, Ayush, for telling me where it is. I've just checked and I've given you the answer.
I have a doubt about the kurtosis. So, as we defined that kurtosis means the fatness of the tails. So, what does it actually means? Like, if it is greater than 3, and I guess 3 is the standard value for that, equals to 3 greater than 3. So, so then it says that it is heavier on the tails compared to normal distribution.
Fantastic. Look at this. You have a uniform distribution. What is a uniform distribution? It's basically a rectangle.
Yeah.
You have the endpoints and it's a flat thing. How will you convert this to a normal?
For uniform distribution.
From a uniform distribution, if something has to turn into a normal, how will it become? What will you do?
So I'm unable to recall it.
No, what is this has not been taught. I'm just asking you a fundamental question. A uniform distribution is a flat line.
Yeah.
How will you make it look like a bell curve?
In a normal distribution, usually we have a mean set at in the middle.
Leave out the statistics. Don't worry about the statistics. I'm just looking at the shape. You have a uniform distribution, which is a flat line. Yes. You have a normal distribution, which is a bell curve. How will you convert this flat line to a bell curve?
So, sir, I have to raise it up from the middle, so as to make it to normal.
You can either pull it like this, or press the tails, and it will come. And just keep pressing, and it will become a mountain, right?
Yeah.
So these are in general. I'm just talking general sense. Now let's look at what thickness of the tail means. So as your normal distribution's tail become thicker, what is going to happen? More weight is going to sit there, which means it's going to be bigger, because your graph is basically a frequency, a bucket number of observations. So when you have thick tails, it is not going to be a beautiful bell shape. It is going to be a fat guy with belly on the side.
Yes, sir.
That is what it means. So you have more chances of having more values on the tails as well, instead of falling on the center. So from a business perspective, if I have such a thing, what is basically going to happen is your variability is going to increase.
So as the spread is increasing, that's why the variance will also increase.
It will also increase.
And for the skinnier tails, what will happen? It will form a sharp normal curve.
It will form a sharp normal curve, which means it's going to be highly clustered around the center and very less along the edges.
Yeah. Then variability would be very low.
Very, very low.
Okay, sir. Thank you.
Sir, I have one general question related to the linear regression. Let's say our target variable or dependent variable is having some close to higher percentage of 0 values. Then naturally that will go through the origin, right? For example, let's say 30 to 40% of the dependent variable is having 0. Let's assume that scenario, and in that scenario, typically, the line may go through the kind of origin thing. In that situation, is a linear regression the correct approach to apply?
Okay, I believe in forecasting terms, linear regression may not be the best technique when you have a lot of zeros, because when you have a lot of zeros, you enter into something known as intermittent demand, lumpy demand, erratic demand, so on and so forth. So that in that case, linear regression may not make sense. So only when you have values, it makes sense.
Okay. So there are. It will be an experimental approach. You can try removing zeros and then try building a regression line.
No, sir. Let's assume 0 is a valid value, valid dependent variable value there.
Yes. Sometimes you might even remove that and then try modeling it. And then you have a train. You split it into train and test. And then if your if you remove zeros and you build a model and your test statistic is better, your model is performing well on the test data, then you can go ahead with that approach.
No, sir. Let's take a
More than-
scenario where a collection scenario, right? For example, if a customer pay back the default amount or not, then technically, naturally, I'll have more zeros, which I cannot remove for modeling purpose, actually.
Here the question comes with respect to what is your X. If your X has, let's say, higher borrowing, less more defaulters, then it's okay, because all of those zeros are going to be clustered in one end. But if it's going to be clustered across, then it becomes a problem.
Okay.
Because ultimately it's a prediction model, right?
Right.
So when you have high defaulters giving zero values, and high borrowers giving zero values, defaulters. In fact, when it becomes zeros and ones, it is usually not a linear regression. It's a logistic. That's a completely different ballgame. But
one way logistics, sir. Other way, how much payment I can expect from defaulted customer? Kind of scenario can happen, right?
Correct. It can happen. That is what I'm trying to say. So then it becomes a ballgame between your X's and Y's. If it's skewed towards one side of your X values, then it's still fair to use, because ultimately the line will go there and hit.
Okay.
And that range of values it might capture. How it captures, it's a different thing, but you will have a lot of errors there.
Okay, got it. Also, sir, in practice, I have seen, like, when we do one of the multicollinearity check in the regression, right? To check if the X variable,
if the X's are related.
Exactly. Typically, some of the X variables we have, like, binary variables, all these variables, but still, in practical sense, people still use that metric. Is it a reliable metric to use in the VAF sense? Actually, I mean, as VAF measures, like, uses a bin variable as a target variable, others as the X variables. Like, any thoughts on that?
I will have to see the context before I give an answer. It is possible to use. That is why people use.
Okay.
But you will have to tell me the exact context with the data only. I will be able to help you further.
Okay.
Swami, you want to add anything? I have not done anything of this sort.
VAF is a very famous approach used in a lot of industrial applications. There are also other approaches to get rid of multicollinearity. You do PCA, principal component analysis, and you do ridge, lasso. So there are many ways. So VAF is again a very commonly used approach for getting rid of multicollinearity.
Like I said, the context matters. Generally, we can't say something is good, bad. It is popularly used. That statement I cannot disagree. But there are different ways of doing it. That is where you come in, and the ChatGPT cannot replace you. Okay, anything else?
I think we did not cover much with regard to quiz and assignment. It was more of a general discussion this time. More into hardcore statistics.
I believe all of our learners are very confident with their quiz.
Yes.
All the best. But you should not come and curse me later. All right? That disclaimer I'll put right away. Right away. Okay. Any other queries?
Not today, sir. Once let us go through week 5 and 6, then again we will come.
Yeah, we'll have a session next week for week 5.
Next week we'll invite Professor Rahul for this session, Malolin.
Sure.
I'll personally invite him.
Okay. Yeah, non-linear demand response.
Yes.
Okay. Optimal pricing, revenue management, revenue maximization, profit maximization. All right. Yeah. Okay, we can have sir come over. Duality and all this.
Swami sir, one question actually. I think at the beginning of the session you mentioned the association between a categorical and continuous variable. Is that topic are we going to cover in the upcoming weeks by any chance?
No.
Okay.
But you have studied it in stats 2, I believe.
Okay. Logically, the two sample t-test is something that can be used, right, in that scenarios or not?
That is for to
measure the association between a categorical and a continuous variable.
You have done it in stats 2. Have a look at
not
it.
In stats, in general I'm talking about actually.
So two sample t-test is used for two continuous variables.
But t-test is used to measure the mean between two different groups, right? There one group has to be a categorical variable, right? Not a continuous, right?
No.
It's a group.
It is between
Group and all the sample values you are taking and you are consuming the mean. of one group with the mean of the other.
Yes.
How can you call it a categorical?
Then technically the group variable should be a categorical variable, right? It indicates the group, right? I mean, just my thoughts.
Okay. No. When I say categorical variable, of course, then everything becomes categorical. In a sense, here we call it a continuous variable because let's say you are measuring weight before and after going to the gym. It's an example, right? So before going to the gym or after going to the gym, this becomes a parity test, but let's not worry about that. Before going to the gym is one group, after going to the gym is another group. So you are calling it as categorical? No. Here you are telling the weight variable is continuous. So it is a continuous variable and continuous variable.
Yes.
Right? So that is how you should see. You should not say that this group, since it's grouped, it's a categorical variable. That is not how it works.
Okay.
No, it's a continuous variable. No, weight is a continuous variable. Yes.
So you're measuring whether weight is changing. You're measuring whether the category of people who went before and after are dependent or independent, or they are related or not. No, you're measuring whether the weight of these people and weight of those people are matching. The people could be same, but weight of this this gymming, the effect of this gymming on weight, is it significant or not, is what you measure. So that it's a continuous variable.
Okay, sir. Okay, sir. I'll check it out. Thank you.
Just think about it. This becomes a continuous variable. Of course, it's for a group, but you're not checking on that group. You're checking on that variable of that group.
Okay. Okay.
Okay.
So pattern will be similar to like previous terms and all, right?
Yeah. MCQs, MSQs, and the thing computation values, short answers. Yes.
The 15 16 questions will be there, right?
I can't tell you that, man.
Okay, no problem.
It's for 20 marks, so.
Okay, sir. Thank you from my side. Good night.
All right. Good night, guys. Okay, if there are no more questions, we can also wind up the session.
Sure. Thank you, Malalan. Thank you all.
Thanks, everyone. See you guys.
Thank you, sir.